So we'll see now properties for two graphs to be isomorphic. So we know that if number of vertices doesn't match, then how can you show the one-to-one correspondence? No, right? That's why number of vertices should be same. Okay, let me list out all possibilities. To say that two graphs are isomorphic, one necessary condition is number of vertices should be same. Okay, number of vertices. What about number of edges? So we know that it's a adjacency, like two graphs should have same structure. For that, number of edges also should be same. So I say number of edges also should be same. If number of edges are not same, let's say, then two graphs are not isomorphic. Second one, it is necessary condition. If number of edges are same, it doesn't mean that structure is same, right? Sometimes what happens, you can draw a graph, two graphs with same number of edges, but in a different structure, right? See, different adjacency. That's why be careful. Number of edges is necessary condition. You should satisfy. If you violate, graphs are not isomorphic. If you satisfy, still graphs may be isomorphic, may not be. So all the conditions whatever I am giving are just necessary conditions, may not be sufficient. Okay, there is no sufficient condition generally. Now number of vertices, number of edges, and sufficient condition is only the definition. What is that? You should show one-to-one correspondence. But I don't want to do that because it is computationally expensive. I don't do that. So I try to find out shortcuts. That shortcuts, check the number of vertices, then number of edges, then check degree sequence. This is one more property of a graph, right? So degree sequence of two graphs should be same, otherwise they are not isomorphic. Again, it is not sufficient. Sometimes there may be graphs with same degree sequence, but again they are different. So that's why go to one more parameter. This is very important parameter. Most of the time it will work. That is, number of cycles. Okay. So just observe the number of cycles and different types of cycles. Check the number of cycles and length of the cycles. I can say length of the cycles like this. Okay. Second one with 5 vertices, let me draw in different way. 1, 2, 3, 4, 5 like this. They give like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And are they same? Are they isomorphic? See, there is a triangle. Here there is no triangle. Don't say that this is triangle because this is not a vertex, right? So here there is a triangle with 3 vertices, but there is no triangle with 3 vertices because this is just crossing point, not a vertex. Okay. Then can you show any triangle in this graph with 3 vertices? No. Then these two graphs are not isomorphic. So easily we can check it. So I will give you a lot of examples to check whether two graphs are isomorphic or not. But observe the properties. One more property you can see, like degree sequence, maximum degree, minimum degree. Okay. You can also identify maximum degree and minimum degree, this kind of things. Then sixth property. So there are so many hundreds of such properties. I'm just giving very important properties. Observe the adjacency of some peculiar, otherwise particular vertices. Example, in your graph, observe adjacency of, I can say adjacency of peculiar. Okay, peculiar vertex. That means a special vertex. Like example, if your graph has a vertex with degree 6, but there is only one such vertex, observe its adjacency. Like example, there is one degree 6 vertex which is connected to like degree 2, degree 2, degree 3. In another graph there is a degree 6 vertex, there is only one, and that is connected to degree 2, degree 3, degree 3, then definitely these two are different structures. Really these two graphs are same. This vertex behavior should be same. What is the behavior of this vertex? It is connected to 3 vertices where one vertex degrees 2, another vertex degree 2, another vertex degree 3. But here it is connected to degree 2 vertex and degree 3 degree 3. How they are same, right? They are not equal. In that way we can check. Understand? Now we'll see some examples of isomorphic graphs. In the GATE exam they give you this kind of graphs. Are they isomorphic is the question. So if you want to number them, you can number them like 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4, 5, 6, 7, 8. Just randomly I numbered them. Now you see, first focus on number of vertices, same. Then check the number of edges. You will realize that number of edges also same. Okay, otherwise you count it. How to count number of edges? I will tell you one easy technique. Sum of the degrees theorem. Apply the sum of the degrees. For that I am listing out all the degrees. Degree 2, 1, 2, 3, 4. Degree 4. This is degree 2, degree 2, degree 2. 1, 2, 3, 4. Degree 4. And this is degree 2. This is 1, 2, 3, 4, degree 4. Apply sum of the degrees 4, 6, 10, 12, 14, 16, 20, 22. So 22 is nothing but twice the number of edges. 2 into E equal to 22, E equal to 11, right? So number of edges in this graph is 11. In that way you can compute. So why I did this one rather than counting directly is so that you can list out all the degrees also. Okay, let me list out all the degrees here. Degree 3, this is degree 3, degree 1, 2, 3, this is degree 2, 1, 2, 3, degree 3, degree 2, degree 3, degree 3, right? Just list out all the degree sequence here. This is 2, 2, 2, and there are some 4s also, right? Like 2, 2, 2, then one more 2, 4 2s, and 3 4s, right? So 12, 14, 16, 18, 8 plus 20, one more 1, 2, 3, 4, 5 vertices of degree 2, okay? 5 plus 3, 8. Here degrees are, there are 2 degree 2 vertices and 1, 2, 3, 4, 5 vertices of degree 3, 6 vertices, sorry, then 3, 6, 18, 20, 22. Sum of the degrees is 22. 22 equal to twice the number of edges, then number of edges should be 11. Yes, number of edges are matching. Sir, why are you counting number of edges in so difficult way? Why not you count like this, 1, 2? But here I observed the degree sequence also, right? So if you see the degree sequence, it is 2, 2, 2, 2. Here it is 2, 2, but followed by 3, 3, 3, 3. When degree sequence is different, then graphs cannot be isomorphic. That's why these two graphs are not isomorphic. I will tell you one more reason why these two graphs are not isomorphic. See the triangles. There is one triangle here, 2, 3. There are 3 triangles, isn't it? But in this graph, I am seeing only 2 triangles. So number of triangles also should match. That's why these two graphs are not isomorphic. Okay. So from now onwards, when two graphs are given, check all these properties, whatever you like in some order. Okay. Generally start with number of vertices, after that number of edges, then followed by degree sequence. If degree sequence also matches, then go for number of cycles and cycle lengths. Two graphs, whether they are isomorphic or not, we'll see. So first we start with number of vertices, 5 and 5. Second, number of edges. So let me list out degree sequence first, so that I can compute edges also, right? So I am listing out degree sequence. Degree 3, right? Degree 3, degree 3. This is degree 2, degree 3. So here degree 3, degree 2, degree 3, degree 3, and degree 3. Now degree sequence matches, right? Whenever degree sequence matches, then I can say that number of edges also will be definitely same, because according to sum of the degrees theorem, sum of the degrees here and here same, but we know that sum of the degrees actually 2 into E, right? Because 2 into E values are same, then 2 will get cancelled. Okay, let's say it is number of edges here E1, number of edges E2. Then sum of the degrees is 2 into E1 here, sum of the degrees here is 2 into E2, but they are equal, right? Because degree sequence is same. Then 2 will get cancelled and number of edges definitely should be same. Otherwise you count them, you will understand. Now, so we have checked 3 things: number of vertices, number of edges, degree sequence. Then what to do? Cycles. So let's try cycles. So there is a triangle here and there is one more triangle here, right? There are 2 triangles I can see. Check here triangles, 1, 2. Even here there are 2 triangles. Let's see any 4 length cycle. There is one 4 length cycle, 1, 2, 3, 4. Any other 4 length cycle? Yes, 1, 2, 3, 4. There are 2 4 length cycles. So here also we have one, second one, one more here, you see, B, D, E, A. There are two 4-length cycles. So whatever I am trying, so whatever the property I am trying, so both graphs are satisfying. Then what to do? Then slowly I am getting confidence that maybe these two graphs are isomorphic. So if these two graphs are isomorphic, then we can, construct one graph from another graph. That means I can redraw a graph so that that will match to another graph. So what is my confidence is, probably by redrawing one graph, we can get another graph. Let's try that. So what I do is, however, degree 2, degree 2, there is only single vertex of degree 2, then E should match with 2, no doubt on that. And remaining 4 vertices, we should observe. Here there is a, triangle attached to triangle. But here if you see other vertices A, B, C, D, can we make this kind of structure? We'll see. So A, D, since this E is connected to A comma D, here this 2 is connected to 1 comma 3, right? Then 1, 3 should have same behavior like A comma C. Okay. Now here 1, 3. So we have A comma, what is that one more thing? D, right? A comma D. So we have BC here. Here you have 4 and what is that one more thing? 4 and 5. So between 4 and 5 you have edge. Between B and C you have edge. Then I realize that the position of C should be, like 5. Then I redraw C here. Then you will understand everything clearly. So I am removing C and I am redrawing it. So draw all the edges from C to anything. BC. Then you add like this. Newly constructed graph now. AC there is an edge. Redraw it. Now BC there is a edge. Then redraw it. Remove this vertex C here. Okay. I am repositioning C. That's it. Not more than that. So I am removing all the edges. Then you get this graph. Is it not, this one? Same, right? So that's why by redrawing this graph, I got it. That's why these two graphs are isomorphic. Understand? Really you want to prove that two graphs are isomorphic, you have to reconstruct the graph like this.